Hello, everyone. My name is YJ, and I already introduced. We are from the MathWorks, who is creating MATLAB and Simulink. Obviously, the MATLAB Simulink we do now supporting ROS and ROS-II pretty a lot. So we have my colleague brought here because one of the topic is pretty new that we're supporting the early this year 2028 release of the MATLAB Simulink. That feature really we have a lot of collaboration with the Heijs, the Horn from the TU Delft in Netherlands. He couldn't make it, but I don't know if he's online or not. But so anyway, today's topic is the automated ROS code generation from MATLAB and Simulink, but also our recent update for the ROS controller generation from the Simulink. Simulink, there are a lot of the control user and control engineer using a lot of Simulink. So, good idea. The Matt actually, the initiate idea is, hey, why don't we, reuse the Simulink coder by generating the ROS controller automatically? And then that controller become the one of the ROS package that everybody can be using. So anyway, that's probably the main topic today. Forward, I don't know why. All right, so I'm gonna start with my talk with a couple of the core that we heard from our customer who are using the ROS with our toolboxes. The one from the Voyage, actually they are developing self-driving car, and also another core from Yaskawa, they are developing the robot manipulator. So what they see is the value of the combination, the combining the strengths of the ROS and also the MathWorks toolboxes together. So ROS, everybody here, ROS is really great. The software architecture they have, the ecosystem the ROS has, but also the MATLAB Simulink is really providing the rich host of vertical speak and the application speak and the specific vertical. But we do also have some kind of a differentiator, which is Simulink, state flow, and verification validation tool. So really, this this is two examples, right? They really complement the traditional the ROS solution and with the MATLAB Simulink, the tooling they have. Another thing, right? Recently ROS become popular industry. Mechanical engineer, as I said, like mechanical engineer, they have a little bit of a limited coding background. They use a MATLAB scripter, and also the Simulink, right? Simulink is really graphic environment, and the mechanical engineer, control engineer, they pretty like that kind of a graphic environment. So but they have a little bit of trouble, right? When they learn the ROS, they have hand coding with the ROS package, the compiling things, and also the building system, and so it's kind of they have some trouble here, but they enjoy really using MATLAB Simulink, and they control thing and making some robot application, and then using our tool like hey, generating code autonomously and then working with the ROS-based simulator and easily to connect with the hardware. So that's what we really see. The more and more, even mechanical engineer, control engineer, they are really using the ROS a lot together with our tool. So with that, I will talking about the why auto coding first, and then I will talking about the generated ROS code automatically from the MATLAB Simulink, and then Abhijeet, he will talking about the ROS controller generation from the Simulink, and then we will summarize and take some question there. So with the MATLAB Simulink, once your system is working as you intended, and then you can now deploy your model by generating code, right? So that means you can really reduce your hand coding error, but also you can really reduce your time to the market, right? So and you need to really spend your more time for your design, but also you need to spend more time for the cool algorithm development, but less time for the coding. That's the idea, right? So, and then the basic idea behind the code generation is you write the code in the very high level language, and then code generator taking that the high level language and translate it to the more in a general purpose program language like a C and C++. So from the MathWorks code generator, we support C code and C++ code generation, HDL, PLC code generation, even GPU code automatically, right? So this is really the important process. And our customer, this code generation really have a lot of role in a different role for their design and development process, right? But many of our in the industry customer, their ultimate goal is production code generation, and then the efficiency is really one of our top concerns. So our goal here is really generated code is really as good as, or even better than your hand coding, and created by experience in a programmer. All right, so, but one important thing that I want to point out is you just design your software once, and then you deploy it to the many target, right? You can deploy your model to the legacy issue, but also you can deploy to the ROS-I application, or also like FPGA, the GPU, the target as well. But another way, right, you can really design SOA, like the service-oriented application, and then you can deploy C++ code, which are compatible with industrial standard, right? So which is like the ROS-I adaptive and DDS and then ROS. That's really the beauty of code generation, right? So, and then now I'm going to talk about the automated code generation from MATLAB Simulink with a couple of examples. So this is very simple, and you do now very complicated, challenging problem. Just so I want to show the very the simple concept. So, okay. So you design your ROS-based application within the Simulink or MATLAB, and then you connect to the ROS network, ROS-2 network in this case, to talk to the Gazebo simulator in this case, and then you're testing everything working in the desktop simulation. After that thing done, you can now start to configure your target system. Hey, where I want to deploy my the ROS code to it, and then you can really set up hey, which target is that your local machine or remote machine, which device it's going to be, the AMD model, or whatever target you specify, and then later on here now the Simulink coder start to generate your ROS code here, ROS-2 code generating your target sheets the target hardware automatically, right? So let me talk about more here. So we have a very tight bridge to the ROS from the MATLAB Simulink. Exactly speaking, not just the bridging, and then we have a really full implementation of the ROS and ROS-2, and then you can really implement the create ROS and ROS-2 application within the MATLAB Simulink, even Windows and Linux, and then you can then have a live connection with the ROS network, and to use the ROS-based ecosystem, and then now you can deploy, right? So here, it's a 3 workflow. You can bring your ROS raw data to the MATLAB Simulink environment, and then you can the playback, right? You can even construct your the scenario based on you load the data with the time series data or the many sensor data together. So that's the one way to use raw data, and then now you can have a live connection with the ROS network to use the simulator or hardware, and then finally you can really deploy to the ROS code to the target system you determine, right? So that's my topic. This ROS code generation and then deployment workflow is really popular in our customer to accelerate the simulation speed, but also they can validate their robot application within the hardware, but also they can finally reduce the error as I mentioned earlier, also reduce their coding time. So we recently make this deployment workflow pretty easy, right? So here, he actually made it. So in the tool strip, you can really determine, hey, do I need to use a ROS-I or ROS-II? You determine, and then you can really specify the hardware, the target hardware the specification over there. And then so you can here you can, hey, do I need to really deploy the local device, local host or remote device? I'm going to tell why local or why remote device later. And then there are multiple options. You can you can deploy your ROS code, just build only or build and execute your ROS node on the target system or in the remote device. And then you can also, when you click the manage your the remote device, you can really specify your target device in the information. Hey, what is my IP address? What is my the source folder gonna be when I deploy the ROS node to it, and then checking workspace, all those things you can specify over it. And then if you have your specific ROS package that you wish to integrate with your generated ROS code, and then you can really, before you generate it, you can really specify, hey, I need to use an OpenCV or other ROS package, and you can really specify, and then you can integrate that code when you generated your ROS code. Before the generation, you can really testing your connection. Hey, did I set up the nice did I set up everything correctly? My IP address is all correct, or all those things you can testing in advance, and then you can see the test your test connection test result can be displayed in the what is that arrow? I don't know what that is. Right. Okay, so in the diagnostic viewer there as well. Right. Cool. And the same thing can be done in the from the MATLAB side, and you can configure in the MATLAB configuration and anything you can set it up, and then you can generate ROS code from the MATLAB the coder using the MATLAB the scripter using the MATLAB coder, right? So here with a 10 line of the MATLAB coder, really become your C++ ROS coder automatically. As I said, there are multiple ways you can deploy your ROS code to your local machine. Also, remote ROS device. As I said, there are multiple ways to deploy the build only and then build and learn as well. So let's say, for example, the ROS device or my robot is not connected yet. So I just deploy my ROS code, and then later on I can manually taking that code to your ROS device. So that's one way to use one of this option. But also build and learn in the locally. Like I have an example here. So this is the build and learn in the locally. So I have deep learning the algorithm is a part of my the application. Then my hardware is over there. my deep learning layer, the module is my host machine that has a little bit of more power, then you can generate, you can generate my code in running on the hardware, my own development machine. And then robot is really giving me my sensor. I can continue sending the data after the deep learning, whatever perception part is done in my local machine. Another way to do it is so this is like you develop your ROS application in the MATLAB Simulink first in the right-hand side, and then you connect to the ROS network to confirm everything working. And then you can generate it, your ROS node, to the remote hardware. In this case, the GPU board, Jetson, and the NVIDIA Jetson board. And then you can really run everything, your ROS node, in that hardware. So in this case, the SLAM algorithm is learning on that, the hardware to navigate through your OPC environment. Okay, so that's my part. The Abhijeet now will talking about the ROS control generator from the Simulink model. Right?
Hello everyone. Thanks Vijay for that great introduction. So what Vijay talked about is basically the full-fledged connectivity that we currently have with MATLAB and Simulink with ROS and ROS-II, which includes node generation, cross back import, and all other kinds of connectivity directly that you can do from MATLAB and Simulink. My talk will mostly involve ROS controller, ROS-II controller generation directly from a Simulink model that you have designed as a ROS controller. So before we jump into the actual application and I show the video of how this whole work comes together, this is a recap from the last slide that was presented in the ROS Industrial Conference of last year by Haish and Brad. So what you are seeing here is basically the ROS driver layered architecture, which basically every ROS control driver is a single process, and multi-threading is basically mostly done to keep real-time, non-real-time context separate. And so what you see, everything below the controllers is all hardware interface layer, and that's what's designed and developed by the OEM vendors. So a robot vendor will provide the hardware interface bits for a driver. It knows how to talk to a hardware directly. However, controllers are the ones who know what to say to the robot. So those are the controllers is where the main magic happens. And here the hardware interface of the robot is actually giving you the transformation of the real world data from hardware to the ROS. So the main part of this controllers are the main logic of this entire system. So that's where your main IP is. And the main part of designing the controllers and manually writing the controller is the problem. And we were approached by Haish and Matt, and then we actually developed this technology to generate the ROS controllers directly from Simulink. So basically, rest of the layer architecture stays the same, but your controllers are now designed and completely developed and deployed from Simulink model, and they now directly talk to your hardware. So example, for this demo, what I'll be sharing is a shape tracing example. And in this, what you are seeing here is a Simulink model, which is basically doing the trajectory following of a few segments, and then you have a simulation part of that. So the main section of this is the controller section that we are going to generate and deploy onto the hardware or your robot. Now, as you see, it's not really a traditional PID controller or model controller, but just to keep it simple, I just to show the actual functionality of this ROS controller generation, I'm going to use this model. So what you do is, this is the simulation model. You use it to validate your controller, and you take your controller and then add more things to it. That makes your actual ROS controller that you can deploy. So as you can see, the blue part, the trajectory generation, it stayed the same between simulation and code generation. That's your crux of that's your basically mind of your controller. And then we added some external interfaces that talks to the outside world. We'll talk about those later on. So basically, you have your controller, and that controller you automatically deploy, and that can be run as a Simulink model on the hardware. So next, what I have is basically a video, and I'm going to talk through this whole process. This video has 4 parts. You can roughly divide it into designing. You're designing the data and designing your controller. Then you set up the controller, set up your model for ROS controller generation. Then you deploy it, and final part is integration. You have your controller. Controller is a plugin. You need to connect it with your final framework, whatever your project is. So we are going to go through the entire process here in this video. So what I'm doing in this case is in this video we are going to design the controller on in Simulink and deploy it on a VM that has a Franca ROS project installed on it. So basically, this entire deployment is happening on the VM. So the first piece, as I said, is to simulate and verify that controller, right? And then for that, basically what we do is you create the 3D data, the shape that you are going to trace in the three dimensions. So you create this shape, and then you can, this is the shape that the robot is going to trace in the 3 dimensions. With MATLAB tools, we have rigid body tree, so you can visualize how the shape looks like in the robot's task space. So since our controller doesn't really have a lot of, it's very simple. We are doing the pre-calculation of IK, and we are converting task space joints, task space waypoints to joint space ahead of time. And so you are doing that, and then finally you have the data. Now you simulate the model. So this is the simulation model that we saw with the trajectory generation, and we have a specific specific kinematic simulation in the model. Once you simulate the model, you will get the end effector position data and joint position data from the simulation. And you get those values and you use them to plot again. So basically what you are doing is you have your controller, you designed it, you simulated it. Now you're going to verify it, how it looks. So you see how it's going to trace. And we also have tools to use the rigid body tree and actually simulate the entire controller movement. So that shows you how you can actually generate, how will it generate the code, how will it generate the code ultimately. So that gives you enough confidence to go further with code generation and deployment part. So, so the next part is basically the Ubuntu machine setup. So what we do here is that we have a Ubuntu machine with all the software installed. We launch the ROS code that will be used later to connect to MATLAB. And I have the workspace here that has the Franca ROS project, and I will use the same workspace to deploy the ROS controller into. And we are going to use these credentials later on. We are going to put into Simulink so that it can use later to deploy the ROS controller node. And now this is the controller model that we modified from the simulation model. So again, the blue part stays the same, exactly the same as the controller. Now we come to the interfaces. So what we have done is, so previously in the simulation model, what we did is it had the constant blocks, constant sending in the joint path segment data. But now we made it more, how do you say, configurable. We have a subscriber here that you can send any kind of joint path 3D space curve data. And you have the input ports that interface to your robot joints. And similarly, you have output ports that send commands to the out to the robot joints. So how do you set this up together? We have a new app called ROS Control Settings, and using this app, you should be able to see the settings that you can perform on the model. So all the input and output ports are now your interfaces. So for example, as you see here, the resource names, you can identify they are from the URDF file that we have from the Franca ROS project. And then we have different kinds of joint interfaces. So currently we support position, effort, and velocity joint interfaces. Currently, I'm just, in this example, I'm just using position joint interfaces. So it's the same thing for all of them. And you do the same settings for input ports and output ports. Next, we come to the parameters. Every controller needs a parameter tuning, right? And with ROS control settings, ROS control generation, we provide dynamic reconfigure parameters here. So you can tune these 2 parameters as shown here and save these settings to the model. As I showed you, we need to now tell Simulink where to download this, how to download it. At the back end, Simulink coder uses SSH, SCP to connect to your robot. So it takes your device address, username, password, folder where you have to put the data, and then it automatically generates the code, packages it, and downloads it on the hardware. So that was the hard part. Easy part of generating code is simply clicking the button. So once you click the button, you should be able to follow the full code generation process in the diagnostic viewer along with the compilation. As you can see, these logs also show the compilation. The code is generated. Now you can view the entire code in the Catkin workspace on the VM. And here's one of the C++ files that you see here. The next part, once you generate the controller, you need to connect the controller. You need to tell your configuration where it is. And that's where we add the configuration. And I'm going to skip through some of the parts here where we have the controller. So once you can see the controller in the RQ Configure app here. And you can also see all the tunable parameters that we added in the reconfigure RQ controller. And finally, once you send the data from MATLAB, you should see the controller start running automatically. So, I mean, this is the single application that actually shows. It was a very packed. It's extremely packed video, so you can tell me. Please talk to us if you have more questions. But this application can be scaled to another industrial applications like welding, sanding, and painting, and many other tasks. So to summarize, the key takeaways are that MATLAB and Simulink provides a really great connectivity for code generation and ROS code generation. It provides you testability, flexibility, scalability for your design work. And you can do multiple iteration of prototyping implementation through Simulink and MATLAB tools. So the call to action is please reach out to us if you want to use this feature or any other feature, and let us know if you want to. Thank you.
Thank you. If I try to one question, any questions for the team from MathWorks? Yes, I can support.
That's in the plans. Please talk to us. We want to do that. So we want people who we can work with and design this. So we work with Haish directly to work on ROS controls. We can work with you on ROS controls.
Yeah. So just for those who didn't hear, ROS2 control is in the works. Answer.
Yes.
Thanks, guys.
Thank you. Appreciate it.
And now shout out to Haish, who's online. So